Hi, I'm Monty Zwiebin, CEO and co-founder of Splice Machine, and I'm here with my colleague Jack Ploshnik to talk about unified machine learning ops and feature stores and model deployment and how these come together to really scale machine learning. And so let's take a look at our organization for the talk. We'll talk about the goals of production machine learning and why these are hard to achieve, and transition to how a feature store makes this easier, and what is the feature store landscape, and what's a fresh approach to feature stores, and how a new approach to deployment with feature stores can really facilitate the scaling of machine learning models in production. So let's take a step back and look at the real-time machine learning components. What's necessary to have a machine learning stack to support real-time applications? Clearly, you need modeling tools like notebooks, experimentation tools like MLflow to keep track of your experiments, deployment mechanisms, often endpoint deployment mechanisms to push containers out that may be making real-time predictions. And underneath this is the new component of a feature store that helps with reusability and governance and serving features, all built on scale out data platforms. Some of the data platforms are necessary for operational workloads, others for analytical workloads. And if you look at the landscape today, some of these are very well taken care of by many vendors in the marketplace, including Databricks and the Spark community, with modeling notebooks and MLflow. But where there really is a gap is the deployment of real-time models and the ability to serve those models and train those models in a very scalable fashion. And that's what we're going to talk about today. So looking at the typical machine learning infrastructure, you usually see teams of data scientists essentially building bespoke pipelines, meaning for each model, and perhaps even for each feature in their model, they're building SQL code, perhaps some PySpark code to facilitate the construction of their model. But their colleagues are doing the same thing. And what ends up happening is that there's a large set of pipelines that are constantly being executed and extracting data from data sources on the left-hand side, from data warehouses, maybe application databases, perhaps real-time events that are taking place in web and mobile applications, and building these pipelines over and over again. And this duplication leads to problems. It leads to higher computing costs because there's so much duplication going on these pipelines. There, on the right-hand side, is this duplicative recreation of features that might be slightly off. One data scientist may have a certain summation or aggregation of sales order revenues, and another one has the same thing, but one included tax, the other one didn't, and these are not quite the same. This is not only duplicative, but partially inconsistent. On the lower left-hand side, lost signal is a hidden problem with this bespoke pipeline approach to building real-time models for a few reasons. One, that you may not be getting the best features that have been fully vetted from both a performance perspective in terms of computational performance or from predictive performance perspective, as well as data leakage, where you're training models on data that really didn't ever occur because of the way you're extracting features in your training examples. And we'll talk about that. And then lastly, on the lower right, being able to go back from a prediction made in a real-time model all the way back to the features used in that prediction, back again to what was used to train the model, back again to what was the state of the data platform that sourced that data and was the source of those pipelines. This is hard. This is really hard for data scientists to keep track of. And a feature store can actually serve to greatly facilitate that. So let's talk about what a feature store is and how data scientists and data engineers can use it. So what is a feature store? A feature store takes data in, either real-time data that are events or batch data from data warehouses and databases, and serves as a single source of truth and a repository that facilitates four main functions. Being able to search for features, being able to create training sets, serving features, and governance. And we'll talk more about these functions individually in a moment. But what the final picture is unlike the duplicative bespoke pipelines that we saw before, you get a cleaner source destination with using a feature store. Now you can build pipelines that extract data from data warehouses, databases, and real-time events, and bring that into the feature store and reuse those pipelines over and over again in models and even in dashboards that may not be using machine learning, but are simply using these curated features that are now available for the whole enterprise to use. So what are the requirements of a feature store? There are many. Just to call out a few, the most important and I think the most challenging elements of a feature store is scalability. Being able to handle features on billions of business entities, and to be able to handle wide feature vectors, perhaps tens of thousands of feature vectors, has proven to be very challenging as companies move from the beginnings of their journey in machine learning to having 10, 20, 50, or 100 models in production. And being able to serve feature vectors, even wide feature vectors, at the millisecond time frame has proven to be very difficult. And one of the most important requirements is point-in-time consistency. And we'll talk a little bit about that nuance, about building training sets that are aligned on time series data. So let's look at the feature store landscape today. Existing architectures for many feature stores take raw data and either ingest that raw data into a key value store, perhaps in a streaming fashion, or in a more batch fashion into an analytics engine, and then use both of these computational stores to serve either training sets or to serve models in real time. And of course, when you have two different computational engines to extract from, it's kind of hard to keep them in sync. And in fact, in existing architectures, these get out of sync. And it becomes difficult to maintain the training sets and the real-time feature serving. And so one approach to solving this problem architecturally with feature stores is to use an HTAP database as a single computational engine underneath the feature store. HTAP stands for Hybrid Transactional and Analytical Platform, meaning it can handle very low latency types of record lookups and range scans, as well as large analytical pipelines. And so you can literally have one engine in the feature store that can be used to find features, to serve features, and to train features. So this becomes a cleaner, more consistent architecture than the previous approaches to feature store architectures. But HTAP databases have proven to be difficult in the past. Some of the challenges of using HTAP databases is that many of the HTAP databases have required the full data sets to be in memory. That's a limitation from both a cost as well as a scalability perspective. Some HTAP databases require specialized hardware that are essentially architected and engineered for the dual workloads. Some of the HTAP databases don't support the full ANSI SQL environment, like having secondary indexes when you want to attack a table from multiple dimensions and still provide low latency lookup, or triggers to be able to trigger functionality upon the changes that are made in the database. And then lastly, many of the HTAP databases are not ACID compliant, but perhaps eventually consistent, where the analytical workloads and the transactional workloads are not fully ACID compliant, meaning that they adhere to the principles of being atomic and consistent and isolated and durable. But the approach that we're going to show today is utilizing an ACID compliant HTAP database to get past some of these limitations here. And the ideas behind this underlying data engine is that first it's scale out. So data is distributed in a shared nothing manner across multiple nodes. It can be deployed on any kind of infrastructure, whether that's on any cloud, including Google and Azure and Amazon, or on premises. It supports full ANSI SQL with the ability to have secondary indexes and triggers, and is fully ACID compliant. And the way it does so is by introspecting any SQL statement and looking at the estimated cost of that statement and making a decision on the fly. Is this going to be a short, low latency statement that may be doing a single record lookup or a short range scan, in which case the query gets compiled after being optimized into bytecode and executed on a very fast key value store. We use Apache HBase under the covers. You don't have to manage the Apache HBase engine in this SQL store. You actually get to use its fast, low latency operations automatically without having to manage it. On the other hand, if you're doing a long training pipeline, a feature engineering pipeline, and you've got lots of joins and aggregations and groupings in your statement, the cost-based optimizer will compile that query into bytecode, but execute that on Apache Spark. So this gives you the best of both worlds there. And so the way we use this implementation of an HTAP database for a feature store implementation is in the following way. For any grouping of features, we call that a feature set, and that feature set is usually describing some business entity. Let's say, for example, a customer. That customer is going to have a primary key so that we can look up the features for that customer really quickly using this HTAP database with a primary key structure. We can look up very quickly the record for a business entity. Now, if you were about to change some of the features, you update the feature set table representing a grouping of features, and under the covers, automatically, a database trigger fires here in the middle that bridges real-time feature serving to a transformation of the old values of those features into a time series representation where there is a primary key maintained and an as of until timestamp that is representing the older values of the feature set. And this is all done automatically. And the reason why this is important is that now on the right-hand side, you have a full versioned history in time series format of all of your feature changes, and you can align training sets using this history. But on the left-hand side, you have a real-time feature set available to serve models in real time with very fast lookups. And we'll see this in action in just a few minutes. Any feature store has a very intuitive API for data scientists. And one example is a single API to create training views and training sets, and another API to be able to get an arbitrary feature vector. So part of the job of a feature store, though, is to essentially tie features to models. And the unified MLOps architecture requires the combination of feature stores with a unique approach to model deployment. And one of the most important elements of model deployment is the ability to have a prediction store so that you have lineage and can monitor for drift of your concepts and be able to compare new models to historical models. So taking a look at what we mean by a prediction store, here on the right-hand side, imagine for every user who asked a model for a prediction, there was a record in the database that had what model they used under the run ID and the features they served for that particular prediction, and then the prediction that came out of the model. If one had one of these memorialized tables for every model, you can go back and easily track drift and easily monitor and govern your models. So one of the mechanisms in our MLOps architecture, which is a unique approach to deploying models, is something called database deployment. And with database deployment, what we do is take any model and serialize that into the HTAP database. And what happens is that the data scientist or the machine learning engineer or just the application developer can just insert records into this evaluation store. And so as they insert records with a record of a timestamp of when a prediction is going to take place, the model that they want to use, and the features for that prediction, and this can be done on a single record basis or in a big batch basis, the database triggers associated with this evaluation store that are automatically constructed deserialize or grab the model from a cache, apply those features to the model, and then memorialize the output here at truly millisecond speed. So this offers a new approach to being able to deploy models and serve models, as opposed to a container approach or an endpoint approach that has a RESTful API only. This is an approach where you can simply use SQL and get the benefits of being able to serve models in real time. So this now becomes a new unified architecture for MLOps, where a feature store is able to both serve your features in real time and perform consistent training of your data sets by tracking feature history, and then using the database deployment in an ML manager to take runs out of MLflow and to be able to deploy them in a database with this full memorialization, enabling you to essentially get lineage and government, where you can go from the prediction that's being made in the evaluation store, find out what algorithm was actually performed or what was used for that prediction and what features were used, go into MLflow with that run ID and find out exactly what features were there, and then dig into those features in the feature store, literally being able to go back to see exactly how that training set was created in a very repeatable way from the creation of the training set in the feature store's automated API. So with that, what we're going to do now is demonstrate this feature store and this database deployment in action. I'll pass it to Jack.
Thanks so much, Monty. In this demonstration, I'm going to show you what Monty talked about, how a feature store can be built on a single HTAP database. So here I'm inside of the Splice Machine platform, where you'll see Jupyter Notebooks, dashboards, you can track your feature store. But seeing as this is the Databricks conference, I'm going to demonstrate the feature store's capabilities on the Databricks platform. Certainly an HTAP database can be connected to wherever you're writing your code, any Jupyter Notebook environment, anything that can accept a JDBC or ODBC connection. Here we're going to use Databricks. So in this demonstration of the feature store and of the capabilities of an HTAP feature store specifically, we're going to build a product recommendation engine. This product recommendation engine is going to have two feature sets. It's going to have a summary of purchases that customers have made over the past day, week, month, year. And then we're going to have a summary of items that are currently inside of a given user's cart. You can imagine they add multiple users to the cart. You're making a product recommendation, and then whatever is in the cart prior to that point is a feature inside of your model. And the training set we're going to use in this model is, was the product that was recommended purchased in this session? Certainly you can imagine wanting to look into a further time horizon, but in this, we're just going to stay all within sort of one user session. So what we have here is two different feature sets, and these feature sets are very different in nature. This first feature set is a batch feature set. This is something that you're going to update, daily or weekly or monthly. This is the type of operation that's coming out of your data warehouse. And with the Splice Machine feature store, this type of operation can be automatically scheduled and managed. What you do is you specify a source. This source can be any SQL database as well as any flat table. You could connect to a Parquet file sitting in S3, anything like that. You bring that data directly into the feature store as a first-class table. Then you have the ability to schedule your transformations on this feature. What start date do you want the transformations to occur? An aggregation window. Do you want this transformation to occur every day, every week, every month? And then you can specify a number of arbitrary feature transformations. You might want to take a particular column and calculate a sum of that column every day or week. And of course, in this area, you can do a number of different transformations, sums, averages, standard deviations, whatever you need to do. And so this first feature set, a batch feature set, can easily be added into the feature store and put into those two separate tables that Monty was describing. Building these types of complex aggregations, even if they're not in real time, even if there's something that happens, just once a week, is not necessarily an easy task. This is the SQL under the covers that the feature store generated in order to populate this batch feature set. And this type of complex SQL, this complex aggregation, is what the data scientists would have to write without the feature store. But now you sort of specify some basic SQL aggregations, and the feature store takes care of the rest. Additionally, because our HTAP database supports triggers, feature transformations can be event-driven. They don't have to be scheduled to occur every week. They can occur whenever a new row of data, a new observation is added to the feature store. What I'm doing here is simply specifying an empty feature set inside of the feature store. I'm writing some pretty basic backfill SQL just to populate that table. And then I'm going to write a database trigger. And this trigger fires whenever a new row of data is added to the database. This is how we're able to build that feature set that uses whatever information is currently inside of a user's cart. Every time a new item is added, the trigger fires and the feature set is updated. So now that we have our feature sets built, we can talk about sort of the first real use case of the feature store, right? Which is building training sets. We have our features, what do we do with them? Building training sets, especially when you have a real-time use case, is not always as straightforward as it seems. And the reason for that is what we call the point-in-time correctness problem. Let's imagine that we want to make a prediction at this time here. We have a given customer ID, we have a given invoice ID, which you could think of as sort of like a cart use, a session ID, the number of items currently in a user's cart, and we have a time that the product recommendation needs to fire. What we need to do to train our model is we want all of the most up-to-date features at this particular point in time. From this feature set, we have this timestamp here, right, which was calculated several days ago. Whereas in this other feature set here, we have this observation when new data was added to, when new items were added to the cart. And this was taken just 30 seconds prior to when this observation occurred. These three different timestamps, which are all different still from the time that a purchase might have actually been made, are what the data scientist needs to wrangle. They need to combine all of these different timestamps in precisely the right way and ensure that they don't accidentally have data leakage. They haven't accidentally included this row here, for example, which occurred after the prediction would have happened in real life. This is a very challenging task to do, and the feature store does it automatically. How does the feature store, how does this work? All a data scientist has to do is they simply specify their training label. They specify their training label, some primary keys and some join keys associated with that training label, and the feature store takes care of the rest. We have this concept of a training view, which is it operates like a view inside of a SQL database. Whenever this is run, the most up-to-date features are pulled out of the feature store and joined in that point in time consistent manner. They can then be displayed to the data scientist in the form of a Spark or a Pandas data frame. Under the covers, what have we actually done here? How did we create, how did this magic of create training view work? What has occurred? the feature store generated this complex SQL statement, which, as you can see, has a number of inner joins, outer joins, subqueries. This is the type of work that is necessary every time a data scientist wants to build a point-in-time correct training set in a real-time use case. They have to wrangle all of these different timestamps, join them together. It's a very time-consuming and error-prone operation. The feature store does it automatically. Now that we have our training set built, we can go ahead and train our model. In this case, we've got a nice little H2O model to do our product recommendation. So now that we have our model trained, it's time to serve features to the deployed model. How do we get features out of the feature store and send them to where they need to go? You'll notice here an API that's probably very similar to what you've seen in other feature stores. We're able to get features out of the feature store in the form of a Spark data frame. We can get them in the form of SQL, which can then be executed. And as you can see, we get features out of the feature store in milliseconds. How this would work in sort of a real-time use case, of course, is you would just parameterize this, right? You can write a little function, get features out of the feature store based on the primary keys that you need, as you can see, in an incredibly short period of time. But what's happening under the covers here is very different than what you'll see in other feature stores due to our HTAP database. The data that's used for training and the data that's used for feature serving are linked with the ACID compliant triggers that Monty mentioned. And so you never have to worry about inconsistency between the two databases. You never have to worry that the data you use for model training is not going to be available to serve to deployed models. These two tables inside of the feature store are linked with ACID compliant triggers, and you can use a very simple API to get features out of the feature store in milliseconds. As Monty mentioned, the feature store can operate as an evaluation store as well. The very same database powering the feature store can deploy models. And this is beneficial because it's much faster. Data doesn't have to move from wherever your feature store is to wherever your containerized REST endpoint is. It's all self-contained within the same ACID compliant system. It's very easy to deploy. There's not another system you have to manage. You have this unified data lineage and governance story. The way this works is we can simply deploy a model using MLflow. In this case, we're in the Databricks environment. We just take that MLflow run ID, deploy a model to the database. What we're actually doing under the covers, as you can see in these logs I've printed out, are we're making a new table inside of the database, and we're associating a database trigger, such that whenever a new row of data is added to this database, the prediction is automatically generated and stored in the very same database table. So if we want to take data out of the feature store and make a prediction based on it, we simply do an insert statement from one part of the database to another. We insert the features from the feature store, and the prediction is automatically generated and stored in the same table in milliseconds. Of course, this doesn't have to be just a single record lookup. This can occur on, in this case, we're doing 19,000 observations, and this happens in just a few seconds. And so the feature store with an HTAP database can power your evaluation store, can power your model deployment mechanism, all in the same system. Finally, putting all of these pieces together, we have an automatic lineage and governance story. We can pull out of the feature store the exact training set that was used in a deployed model. We can then pull out all of the predictions that the deployed model has made, who asked for those predictions to be made, when, what model was used to make those predictions, the predictions themselves. And then we're able to make a plot that looks like this. We're able to track the distribution of features that the model was trained on and compare that to the distribution of features that the deployed model has actually seen. And so finally, putting everything together, what myself and Monty have talked about today is a complete unified architecture. The HTAP database can modularly fit into whatever architecture you have and solve all of the missing components that are necessary for real-time machine learning. And so with that, thank you so much, and we will happily answer any questions in the chat.